In this project presentation, we will be looking at the Leidenfrost effect, which plays a significant part in phase changes in heat transfer processes.
Most of us should have come across one of those videos floating around on the internet in which a person quickly dips his hand across a flowing stream of molten metal without any injury. It seems like sorcery at first, but there is a definite scientific basis behind this, relating to phase changes and heat transfer. To start off, when we think of phase changes, we usually understand them to be a normal occurrence at a specific temperature and pressure based on the laws of thermodynamics. But what happens when a liquid comes into contact with a surface that has a temperature much greater than the normal boiling point? We would expect the liquid to vaporize almost instantaneously, but instead, we observe the Leidenfrost effect. The Leidenfrost effect, aptly named after the German doctor Johann Gottlob Leidenfrost, is a physical phenomenon in which a liquid produces an insulating layer of vapor that prevents the boiling away of the liquid at a rapid rate. But what does this really mean besides the jumble of words that seems to make sense? Take, for instance, this droplet of water on a surface. At room temperature, this droplet of water isn't doing much, since there is no temperature gradient that allows for heat transfer, except maybe a bit of evaporation at the surface level. If we were to raise the temperature of the surface steadily to a temperature just below the boiling point, the droplet flattens since the surface tension of water decreases with increasing temperature and begins to evaporate due to conductive heat transfer. At a temperature greater than the boiling point, the droplet hisses and evaporates quickly due to a greater amount of conductive heat transfer occurring. However, at the Leidenfrost point or above it, approximately at around 193 degrees Celsius for water, the droplets coalesce into small balls of water that skitter around the surface, existing as liquid for a longer period of time than either of the two scenarios aforementioned. When a liquid comes into contact with a surface above or at the Leidenfrost point, the bottom surface of the liquid vaporizes immediately upon contact with the surface. This vapor at the bottom suspends the rest of the droplet above it, creating an insulative layer that prevents any direct contact between the liquid water and the heated surface. From this, the conductive heat transfer is impeded significantly by the layer of vapor that formed at the bottom, since vapors have much less thermal conductivity compared to the surface. Since heat transfer is slowed down due to the presence of the vapor at the bottom of the droplet, the liquid droplet is able to move around the surface on the vapor beneath it due to the vapor's own vapor pressure that keeps it suspended above the surface. Because of the vapor layer that prevents direct liquid-solid contact, this causes film boiling to occur, which is stage 4 of the boiling regimes. To observe and understand how the Leidenfrost effect works, we will be experimenting with the behavior of water in different temperature conditions and measuring how long it takes for water to evaporate completely at each temperature. We placed a 1 milliliter droplet of water on a hot plate and measured the time required for a phase change to occur or for the Leidenfrost effect to be exhibited. In the first run, we used a hot plate temperature of 85 degrees Celsius. The total evaporation time taken was greater than 60 seconds, almost taking another 50 seconds to start boiling slightly. In the second run, we used a hot plate temperature of 100 degrees Celsius. The total evaporation time taken was greater than 60 seconds, but nucleate boiling was observed at 15 seconds. In the third run, we used a hot plate temperature of 130 degrees Celsius. The total evaporation time taken was 22.3 seconds, and nucleate boiling was observed immediately upon dropping. In the fourth run, we used a hot plate temperature of 160 degrees Celsius. Total evaporation time here taken was 8.24 seconds, and the droplet began boiling immediately upon placing. In the fifth run, we used a hot plate temperature of 193 degrees Celsius, which is the recorded Leidenfrost point for water. The total evaporation time here taken was 4.63 seconds with immediate boiling. In the sixth run, we used a hot plate temperature of 195 degrees Celsius, which is slightly above the Leidenfrost point. The total evaporation time taken was 5.28 seconds, and we could observe some of the droplets showing the Leidenfrost effect. In the seventh run, we used a hot plate temperature of 220 degrees Celsius to see if the Leidenfrost effect would be improved. Total evaporation time taken was 4.13 seconds, and the Leidenfrost effect can be clearly observed for the droplet. Based on our experimentation, we observed a trend. The Leidenfrost effect definitely increases the time of our water droplet to remain in liquid state, but at temperatures much greater than the Leidenfrost point, the radiant heat flux from the vapor film becomes more significant, and heat flux increases, which results in a shorter time required for evaporation to occur. This can be observed clearly in this graph, as we see that the water took the shortest amount of time to evaporate at 220 degrees Celsius. Conclusively, this data meets our originally expected outcome in how the Leidenfrost effect allows for a longer time needed to evaporate, as the added layer of insulation around the droplet hinders conductive heat transfer from occurring to allow phase change to occur. Although we can observe the Leidenfrost effect mostly in our kitchens, applications of this effect are still under research, as some of its uses include high-sensitivity mass spectroscopy and in prototype heat engines as of now. Perhaps in the future we would be able to harness this effect for various purposes that require minimal friction in fluid systems. This ends our group project presentation on the Leidenfrost effect. Thank you for watching.